All right, so we're going to go through this today with some review on chemical reactions, the process by which one or more substances is turned into different ones with different physical and chemical properties. And the reasons that things react is to fill up their valence electrons if necessary, or secondarily, to become more stable, meaning they have a lower potential energy level. Right. These sentences are what represent our reactions, and we'll use those to identify our reactants and products as we go through this. You've seen word equations already. That's where we've got them all written out as longhand words. And then last week, we converted some of those word equations to formula equations where you just have the formulas written. But that's not quite the end of chemical reactions for us. We need to then convert them to balanced chemical equations, in which case each of the elements that are in our reaction are balanced. They have the same number of each atom on both sides of our equation. Right? And our chemical reaction is just going to record that. This is the process by which substances are changed into different substances. Your reactants are what you start with, and your products are what you end with. Okay. To bring back some stuff that you probably talked about in middle school, these are the evidences that we have that chemical reactions have taken place. Light can be given off. Most common, heat is given off or absorbed. So it either gets hot or it gets cold. A gas is produced and there's a change in color. All of these are evidence for reaction. To verify a reaction, you must check the chemical properties. We are not going to do that in this class, but starting your next chemistry class, often you will verify what the products are by checking properties like melting point and things like this to determine that you have the substance that you have intended to isolate. Okay? For chemical reactions to occur, there's a couple things that have to take place. The molecules themselves must collide with each other. Okay? They have to collide with enough energy that they don't just bounce apart, but that those atoms interact with each other. And they have to be oriented the right way, or they'll just bounce off of each other, right? So these are very necessary steps that have to take place. The molecules have to hit each other with enough energy and be oriented in the right way. Otherwise, the reaction won't occur, okay? And then chemical reactions will release or absorb energy. So I'm going to talk a little bit more about exothermic and endothermic reactions in this graph that you have seen, right? Exothermic reactions occur when energy is released. If energy were a thing that we recorded in a chemical equation, it would be in the product. For instance, in this example, we have nitrogen dioxide reacting to form nitrogen and oxygen, and here is the energy that's given off in this reaction. If it's plotted out on a graph like this with potential energy here, right? The NO2 has a certain energy. The N2 and O2 have less energy. The difference between these is the energy that's given off by this reaction. Okay? Delta H means the delta, whenever you see a delta from now on in chemistry, biology, physics, whatever you're doing, delta means change. This means change in something called enthalpy, which is a fancy word for heat, thus the H. Okay, so this means change in heat. It's always the final amount of heat minus the initial amount of heat, right? And delta H is negative for an exothermic reaction. You could think of it as exit, same root, right? Same prefix, means to leave, okay? So in this case, a low number minus a big number gives you a negative number, right? And so our delta H is negative in an exothermic reaction. The hill is the activation energy. In an exothermic reaction, your activation energy is not very big. It's easy to get the reaction to go in that direction. Okay? For an endothermic reaction, energy is absorbed, and if we wrote energy as part of our reaction, it would be on the reactant side. So the reverse of the last reaction, right, is N2 plus O2 plus some energy gives us our N2O. Okay. In this case, the things I start with have a low energy, the things I end with have high energy, and there's a much greater activation energy, which is why it's more difficult to make the endothermic reaction occur. Okay. In this case, delta H is always final minus initial. The final is a big number minus a smaller number. That always leaves us with a positive value. So your enthalpy will be positive in an endothermic reaction, right? And again, a much higher activation energy for an endothermic reaction. Right? So in a chemical reaction, mass is neither created nor destroyed. The atoms don't get added or taken away. We have to keep track of all of them and make sure we have enough of them so that there aren't atoms just like left over and hanging around. You know, you get a Lego set and they always have some extras at the end. You can't have any extras in this, all right? Number of each atom before a reaction must equal the number of atoms after a reaction, and that's why we balance equations. Okay. Let's see, that's a redundant slide. Here's what you're going to go through, right? As you do this, if you need it all written out in directions, here you go, right? You're going to write formulas down if you don't have them, right? Then you're going to complete some kind of an atom inventory, right? On this side of the reaction, I have a sodium. On this side of the reaction, I have 2 sodium, right? Something like that where you're going to keep track of how many you have. Then you're going to adjust the coefficients, right? Those are the numbers that come in front of the formula, right? Until you get those atom inventories. So you'll change the coefficients and then check it with another atom inventory, and you'll go through this several times as you balance each equation. You guys will get pretty fast at it and be able to do most of it in your head. Okay? Coefficients are the numbers in front. They are not the subscripts. Don't change the subscripts. That changes the formula of the compound you're using, and we can't do that, right? We need to change the coefficients because we need to satisfy the law of conservation of mass, okay? So let's go through a couple of them. All right. KClO3 reacts to form KCl and O2. If I divide this right down the middle, okay, what do I have on this side? Well, I've got 1 potassium, I have 1 chlorine, and I have 3 oxygen. Okay? On this side, I have 1 potassium, 1 chlorine, but I have 2 oxygen. Okay? I do not have a balanced equation because I don't have the same number of each type of atom on both sides, right? I know from this that I'm going to need more oxygen on this side. The only way I can get more oxygen is with more of these. So instead of 1, now I have 2, right? Then I have to do another atom inventory and sort it out. So here this gives me 4 oxygen, right? 4 oxygen. Well, now I need more over here, right? The only way I get more oxygen over here is by changing my coefficient, right? So now instead of 1, I have 2. That's going to change all these numbers for me. So now I'm going to have 2 potassium, 2 chlorine, 2 times 3 is 6 oxygen. Okay? That tells me I'm going to need more oxygen over here, right? I can get 6 if I put 3 up here, right? Now I'm going to have 6, right? So I now have K and Cl that each need 2. I only have 1 on each side, but if I double this one, okay, now the number of each atom on both sides is the same. So this is our balanced equation. I'm going to need 2 of the KClO3 formulas. They will react with each other to form 2 of the KCl's and 3 oxygen molecules. Okay? In your chemical reactions assignment, we want you to model your reaction. Here's what that's going to look like. Okay? I'm going to model this one for you, right? I have a potassium and a chlorate ion, right? There's my potassium. There's my chlorine. My chlorine is surrounded by 3 oxygens in that chlorate ion. That's going to attach to one of those oxygens. That's my potassium chlorate molecule. I have 2 of them. Right? So now I have 2 potassium chlorate molecules. Those are going to react to form 2 KCl molecules, right? My potassium is green and my chlorine is yellow, so I'm going to need those over here. There's a potassium chloride, there's another potassium chloride, right? Those are going to give me then 3 oxygen molecules. The red ones are the oxygens. There's an oxygen molecule, there's an oxygen molecule, there's an oxygen molecule. Okay, so we've modeled here that these 2 things will react with each other to form 2 of these and 3 of those. Okay, so you can do this digitally, or you can take a picture after cutting out circles in paper, or how, you know, there's 1,000 methods you could do to represent your reaction on your report. This is what we mean by modeling it. You're going to give us a balanced equation. You're going to show us what those molecules look like and how they react. Okay. So, and you can do this with, you can have an arrow, you know, plus, and finish it off that way. Okay. So that's all we're looking for the modeling section, is for you to understand what molecules you have and how they're going to form your products. Okay. Let's do this one. Right. Again, I'm going to divide this in the middle, right? On this side, I have 1 magnesium, 1 hydrogen, and 1 chlorine. On this side, I have 1 magnesium, 2 chlorines, right, and 2 hydrogens. Okay? In this case, right, my magnesiums look like they're okay, but I have 1 hydrogen and I have 2 hydrogens. If I double this, that changes my numbers here, right? And now they match. That's easy. Okay, so now you have a balanced equation. Just by writing it, you indicate that there's 1 of each of those. We generally don't write the 1. There is one part of your assignment today that will ask you to put a 1 in, just to ensure that you know that by writing it down there's 1. But after today, you can leave the 1 off. Just writing the formula down tells me there's 1 of them. If you need more than 1 of them, coefficients. Okay? Questions on that? All right. Here's some more. Okay. Let me give you a hint on these, right? There's oxygen in everything. So trying to combine them all will make your life more difficult as you try and adjust them. But notice, if you keep track of your polyatomic ions, right, we know that nitrate shows up on this side and nitrate shows up on this side. If you count the polyatomic ion as a single thing, it's a lot easier to keep track of this and to balance it. So in this one, right, I have 1 iron, but I have 3 nitrate ions. Okay, I have 2 sodium ions and I have 1 CrO4, 1 chromate ion. Right? On this side of the reaction, I have 2 irons and 3 chromates. Right? And then I have 1 sodium and 1 NO3. So by keeping those together, it'll be easier for you to balance your equation because you can adjust those because they show up on both sides. But if they don't show up on both sides, then you have to do it the other way. But when they are, then it's just easier. Okay, so if I have 3 chromates on this side and I'm going to need 3 over here, I need a 3 there. Okay, that's going to give me 3 of those and 6 of those. Okay, this tells me I have 2 irons. I'm going to need a 2 here, right, to get those 2 irons. Right, that's going to give me 2 times 3 is 6 nitrates. Right? If I look over here, I have only 1 nitrate, right? If I'm going to get 6 of these, I'm going to have to deal with 6 of those. That's going to change my sodium, right? And now I have the same number of each type of atom on both sides. All right? Here I've got 1 carbon, 4 hydrogens, 2 oxygens. On this side, I have 1 carbon, 2 oxygens, 2 hydrogens. This is 1 oxygen. I don't have a polyatomic ion on this side, so I have to combine my oxygens here. Okay, so this will be 3 oxygens. All right. Now, the difference between here and here is 2 hydrogens and an oxygen, right? So I have 3 oxygens here. The only way I get more here, right? But that's going to change this up to 4. Okay. I've only got 3 over here. I can get another one if I add one of these. Right? That's going to give me another oxygen. So this will go up to 4. But that's also going to double my hydrogens and make that 4. Okay? And now I have the same number of each type of atom on both sides. That's a balanced equation. All right? All right, there's a question in the chat about we have to add more molecules. Where do those come from? Okay. They come out of your head because you have to balance the equation. In an actual reaction, you will have in even the smallest sample billions of these molecules reacting. What you're determining by balancing the equation is what ratio they will react at. Okay, so that when you do the lab in a lab setting, you'll know how much of your product you should be getting because you'll use those ratios later. For the purpose of balancing the equation, right, we're just pulling those numbers out of our head because we don't know until we've balanced it what ratio they will react, but they will react in this ratio, right? It will require 2 of these and 3 of these to make this reaction go. Even though you've got hundreds of billions of reactions taking place in the little beaker that you have, right? We can count those, and when we get through balancing equations and predicting products and reactions, we'll get into that math where you can weigh something and then tell me how many atoms it is and how much of the product you're going to get, right? We'll get into that. But for right now, you're just adding the number of molecules until you get the numbers right so that you have a ratio that will work, right? And then when you do the reaction in the lab, the numbers that you see here and the math that you write down will match what you see in the lab. Let me know if that answers the question. All right. Now it's your turn. Here's 2. Give them a shot. I'll go over them in like 3 minutes. All right, let's go ahead and go through this. I do my atom inventory. I have 2 hydrogens and 2 oxygens on that side. And on this side, I have 2 hydrogens and 1 oxygen. Okay. I need more oxygen on this side, so I change that. That gets me 2 of those, but 4 of that. I'm going to need more hydrogen over here, so I can double that. That gets me 4. Now I have the same number of each type of atom on both sides, so that's my balanced equation. Okay. For this one, I have 2 sodiums, and I have a carbonate ion. I have 1 aluminum, and I have 3 hydroxide ions. On this side, I have 1 sodium and 1 hydroxide. I have 2 aluminum and 3 carbonate ions. Okay, so I'm just go ahead and start at the beginning. I have 2 sodiums. I'm going to need 2 sodiums over here. All right, so that's going to be a 2. That's going to give me a second one of those. All right. I have 1 carbonate. Oh, I have 3 carbonates over here. I'm going to need 3 of these. Okay. That's going to give me 3 carbonates, but then this has to change. All right. That's going to be 6. Okay. Well, that means I have to change this again. All right. If I'm going to need 6 of those, I got to change that to 6. So then I'm going to have 6 sodiums and 6 hydroxides. Okay. If I need 6 hydroxides, I'm going to need 6 here too. So that's going to have to be a 2. Right. That'll change this to 6 hydroxides and 2 aluminums. Oh, good. That's what I have over here. 2 aluminums, 6 hydroxides. So everything works out. Right.